In Chapter 18, we're going to be looking at aldehydes and ketones. This is a continuation of our discussion of carbonyl compounds. In Chapter 17, we talked about carbonyl compounds, sort of an overview. And now we're going to specifically look at some of the relevant reactions around aldehydes and ketones, what you can do with them, how do you make them, and a variety of things related to aldehydes and ketones. So let's get started. So as far as aldehydes and ketones go, and this is going to be true, this part is going to be true for all of the carbonyl compounds, is that they contain a carbonyl group. The big difference is with an aldehyde, you either have two hydrogens or you have a hydrogen and a carbon. And with ketones, you have two carbons attached to that carbonyl. With other carbonyl compounds, we're going to have other things that are attached, either an oxygen or a halogen or even a nitrogen. So there are a variety of different things that could be attached. We'll find that there are two most important structural features around aldehydes and ketones are going to be, one, that the carbon is sp2 hybridized and relatively uncrowded. We can approach with either a nucleophile of some sort, or some nucleophile of some sort, or we can even attack the oxygen. But a nucleophile can come in and attack that carbon because it is relatively unhindered. And the other feature is that the carbonyl carbon is electrophilic. The carbon-oxygen double bond is quite polar, and that causes there to be a significant partial positive charge on the carbon, which means that we can do reactions at that carbon. And that's going to be the basis of many of the reactions that we will look at here in Chapter 18. Now, we did look at some of these back in Chapter 17, so some of this is going to be review, but some of this will be new. So when it comes to the reactivity of aldehydes and ketones, we'll find that they both are very good at reacting with nucleophiles. They both have a significant partial positive charge on the carbonyl carbon. However, we're going to find that there is a difference between the aldehydes and the ketones. Aldehydes, and we'll start with formaldehyde. Formaldehyde has very little steric hindrance because the hydrogens don't take up much space, and because they don't add any electron density to that carbon. And so aldehydes, like formaldehyde, is going to be the most reactive. Now, regular aldehydes, where there is one alkyl group and one hydrogen, those are going to be slightly less reactive than formaldehyde, but still fairly reactive. And then finally here we've got ketones. Ketones have the two alkyl groups. The alkyl groups do make it a little bit more sterically hindered, and they add electron density to that carbon, stabilizing that carbon to some extent. So we'll find that the ketones are going to be somewhat less reactive than the aldehydes, but they're all fairly reactive carbonyl compounds. So let's go look at number 2 on the in-class assignment. So we'll switch over here. And here we've got two aldehydes, and we want to explain the reactivity difference between these two aldehydes. So we want to say, why is benzaldehyde less reactive than cyclohexane carbaldehyde? Well, why is that? What is it that causes that difference in reactivity? Well, benzaldehyde, when we look at the partial positive charge that's on the carbon, we'll find that the benzaldehyde has these pi electrons in the benzene ring that can donate and delocalize that partial positive charge on that carbon. And as a consequence, because it delocalizes that partial positive charge, it makes it less reactive. It makes it less reactive. So again, we're going to say delocalized electrons partial positive charge on our carbonyl carbon. All right, so it makes that partial positive charge delocalize as well. All right, so that's delocalized electrons make the partial positive charge on that carbon more delocalized itself. And that's what makes the benzaldehyde less reactive. That's our rationale behind that. All right, we're going to do a brief section on nomenclature for aldehydes and ketones. And we've got two ways of naming it. We know that there's the IUPAC nomenclature, and then there is a sort of wide variety of common names that we can have. We're going to start with the IUPAC nomenclature, but it's hard to get away from the common names, so we'll talk about the common names as well. If we want to name an aldehyde, just a normal aldehyde, using the IUPAC method, we're just going to change the ending at the end of an alkane from E to al. So for example, pentane becomes pentanal, like this one. Propane becomes propanal. Right? So that is the typical way of doing that. If you have a CHO group, which is the aldehyde functional group, and it's bonded to a ring, then we're going to name the ring and then just add the words carbaldehyde to the end. So for example, if we had a carbonyl on a cyclohexane ring, we would call it cyclohexane carbaldehyde. And then if we have a ring, we're going to number. If we have a chain, we're going to number that chain starting at carbon number 1, where the carbonyl is. And if it's on a ring, then we'll number that. Well, we don't have. If it's on a ring like cyclohexane carbaldehyde, then the carbaldehyde is assumed to be at carbon number 1 on that ring. We don't have the actual carbonyl for an aldehyde within a ring because then it wouldn't be an aldehyde. All right, so we usually omit the number from the name because if it is on a chain, it has to be at the end of that chain. So it's always assumed to be carbon 1. So this ends up being 2-chloropropanal. This one, so 1, 2, 3. On the third carbon, we've got a methyl, so that's 3-methylpentanal. And then this one is phenylethanal. And so here is the ethanal, and then here is the phenyl group that is attached to the ethanal. Since there's only one place that you can attach that and it still be an aldehyde, then we don't necessarily have to put a number there. It's just phenylethanal. Now you'll notice here below we also have some common names. So propanal in the common nomenclature is called propianaldehyde. So this would be alpha chloropropianaldehyde. So that is a different way of naming it. Pentanal has the name valoraldehyde. So the valoraldehyde, when we have a methyl on there, we would call this beta-methyl valoraldehyde. You can see why we kind of like the names pentanal and propanal because those have the systematic names and we know the numbers that go with them. For ethanal here, we can also call this one phenylacetaldehyde. Acetaldehyde is the common name for this component for ethanal. So let's look at some of those common names and just to distinguish. So like carboxylic acids, like a whole bunch of other different compounds that we have talked about, we're going to find that that aldehydes have common names. And so the simplest aldehyde is called methanal according to the IUPAC nomenclature. However, very few people ever call this formaldehyde. And the reason we typically don't call it, or very few people call it methanal. Almost everybody calls it formaldehyde. Sorry, I messed that up. So almost everybody calls it formaldehyde. And that's just because that is the name that is commonly used. All right, so the way that we do this is we take the common name parent and we just add aldehyde to the end. So this is an acetyl group, and if we change this to an aldehyde, it's acetaldehyde. Again, the IUPAC nomenclature is simply ethanal, but most people would refer to this as acetaldehyde. If we look at the IUPAC nomenclature for this one is actually simpler with the common nomenclature. So the IUPAC nomenclature is benzene carbaldehyde. So we've got a benzene with a carbaldehyde functional group on it, benzene carbaldehyde. But the common name for this is benzaldehyde. All right. If we use the common nomenclature, then we often will use Greek letters to indicate where the substituents are. Those Greek letters, alpha, beta, gamma, delta, and you can go further. You can go to the other Greek letters, epsilon, zeta, eta, theta, and good. I mean, if you know the ones past that, good for you. Mostly we'll use those first 5 or 6 Greek letters. We don't typically go much further. Often for the very end, we'll call that the omega carbon, and we'll talk about that more when we're talking about carboxylic acids and their derivatives, but it is true for aldehydes as well. So we can use the alpha, beta, gamma, delta for indicating where substituents are. All right, for our ketone nomenclature, we're going to start with the IUPAC nomenclature. We want to find the longest continuous chain that has the carbonyl group and then change the ending from E to -one. So for example, butane becomes butanone and pentane becomes pentanone. So this would be a pentanone group because we have 1, 2, 3, 4, 5 carbons in that group. Now we do want to number the carbon chain to give the carbonyl group the lowest possible number. In this case, it doesn't matter which side we number it from. That one's going to be carbon 3. However, when we apply the other rules of nomenclature, that means that we need to count from the right side. So 1, 2, and that gives this substituent the lowest possible number. So 1, 2, 3, 4, 5. That means that this is pentanone, and it's got the -one at the 3 position. And like we do with alcohols, we're going to put the number immediately before -one. So we would call this pentan 3-one. And then finally, we have a methyl at the 2 position, so it would be 2-methyl pentan 3-one. All right. With cyclic ketones, we always number starting at the 1 position, but the 1 is usually omitted from the name. So for example, this is cyclohexanone, and we would number this as carbon 1, and then we would indicate the numbers 1, 2, 3, counting counterclockwise because we have a substituent going this direction. So we'd put that one at carbon 3. We can put the rest of these in here. So we have a 3-methyl cyclohexanone. Now you'll notice that we don't put a 1 for the -one because it's implied to be 1. If it's cyclohexanone, it's implied to be at position 1. If you get a diketone, you would number them. So like if you have a dione, you would number it. So let's look at some common names of ketones. So most of our common name for ketones are going to be by taking the ketone, so the carbonyl is in the middle, and then you put the substituents that are attached. So, for example, the IUPAC name for this is butan 2-one, although most people just call it butanone because there's no other possibility. If it's butanone, there's really no other way to do it. So most people call this butanone, but we can refer to this as what's attached. We've got a methyl group attached to the left and an ethyl group attached to the right, as you can see over here. And then we just put those in alphabetical order. So we would refer to this as ethyl-methyl ketone. All right. To make matters a little more complicated, often when these things are sold, so for example, it used to be you could just walk into any hardware store and purchase some ethyl-methyl ketone, but they didn't sell it as ethyl-methyl ketone. They sold it as methyl-ethyl ketone, and then they would often abbreviate it as MEK. Well, that, of course, is a different way of doing it, but that is, the common nomenclature sometimes gets manipulated for an even more common approach to naming things. So we would probably just call this 2-butanone or ethyl-methyl ketone. Both of those are going to satisfy this particular class. But like I said, if you go into a hardware store and you need some MEK, then they're going to help you out. Although a lot of places have stopped selling it. There is a fairly significant toxicity. It's a solvent that's used. It's a little less volatile than acetone, but it also has a little bit higher toxicity than acetone. So to limit exposure to workers, some places have stopped selling it. And they've started using alternatives like ethyl acetate as an alternative to that. Ethyl acetate is a lot less toxic. All right, there are some commonly used names for certain ketones that I want to discuss. So for example, propanone is most often called acetone. And most people have heard of acetone, even if you're not a chemist. If you're sort of aware of things that are in the products you buy in your home, you probably have heard of acetone. It is used as a paint stripper, but it is also used for removing fingernail polish. So it's the most common ingredient in fingernail polish. Here we've got acetophenone, and acetophenone is where you have a methyl and a phenyl group attached to the carbonyl. So methyl phenyl ketone is acetophenone. And if you have two phenyl groups attached to the carbonyl, we refer to that as benzophenone. So that gives us some interesting names that we could call this. Our IUPAC nomenclature for this one, we actually did this one a minute ago on the previous page. It was the 2-methyl pentan 3-one, but we could also refer to this as it has an ethyl and an isopropyl group. Ethyl comes first alphabetically, so we would call this ethyl isopropyl ketone. Personally, I like the IUPAC nomenclature when doing this kind of naming of a ketone, but I do want you to be aware of the other nomenclature you will see. So this is an acetophenone derivative. If you name this after acetophenone, you could say we've got acetophenone with a bromo group at the 3 position, and therefore we could call it 3-bromo-acetophenone. Or we can use the ortho-meta-para designation to indicate that this is meta-bromo-acetophenone. If we have an acyl group as a substituent, either an aldehyde or a ketone as a substituent, we can use these names to name those substituents. So like if you have you have one of these on a ring and you've got some other stuff attached, you just want to name this component. Here we've got formal groups. A formal group is where we have a CHO group that's attached to something. It's not part of the main chain. So that's for aldehydes. If you've got a CH3O that's attached, that's an acetyl group. And then if you have a phenyl with a ketone, so the phenyl with a carbonyl attached to it, that is the benzoyl group, benzoyl. Now, one thing that I want to mention about this is that I don't want you to confuse benzyl with benzoyl. They are very similarly spelled, but they are different. Benzoyl is specifically when we have the carbonyl and the phenyl group attached. Benzyl is when we have a benzene ring and a CH2, and then that is attached. And one way to kind of help you remember this, although be careful with this, one way to kind of remember the difference between benzoyl and benzyl is that benzoyl has an O, so it has the oxygen, and benzyl doesn't have the O, so it doesn't have an oxygen. All right, hopefully that doesn't confuse you with some other substituents, because things will get weird later when we look at some other substituents. All right, one last thing before we go on to our nomenclature problem on our in-class assignment. When we're naming compounds that have both a carbon-carbon double bond and an aldehyde, or a carbon-carbon double bond and a ketone, we have these special names for them. So if it's got the carbon-carbon double bond and an aldehyde, we're going to refer to that as an enal. Now, the aldehyde is always at the end, so we don't need to put a number for that one, but we will need to put a number to indicate where the alkene is, where the ene component is. If we've got the carbon-carbon double bond and a ketone, we have an enone, and we'll have to put numbers for both the alkene and the ketone to indicate where those substituents are. And then we number the chain to give the carbonyl the lowest number. So looking at this first one, we've got 1, 2, 3, 4 carbons in this, so it's butanal. But if we look at the third bond in that carbon-carbon chain, so 1 to the third bond, there's an alkene, there's a double bond, so we'll put an ene. So it's but3-ene-al. So but3-ene-al. And then, of course, we've got 2 methyl groups attached. So that gives us 2,2-dimethyl but3-ene-al. For ketones, again, we want to number from the side that gives the carbonyl the lowest group. So 1, 2, 3, 4, 5. We've got a methyl at the 4 position. We've got the ketone is at the 2 position. So you'll see we put 2 in front of the one. And then if we count the bonds, 1, 2, the third bond here is the carbon-carbon double bond, so we'll call 3-ene. So this becomes 4-methyl, pent, 3-ene, 2-one. All right, so let's look at number 40 on the in-class assignment. So we'll switch over to number 40 and look at our document camera here. So we want to give the IUPAC nomenclature for each of these. I'm going to move my camera a little closer. All right, sorry for the jump cut there. All right, so we want to give these each their IUPAC nomenclature. So let's start with numbering it to give the correct position. So this is a ketone. That's going to be carbon number 1. We want to give the next substituent the lowest possible number. So that's 2, 3, 4, 5, and 6. So that means we, at the 2 position, we've got a methyl. And at the 5 position, we have an ethyl. So when we put those in alphabetical order, the ethyl is going to come before methyl. So it'll be 5-ethyl, 2-methyl, cyclohexanone. All right. And so that is the proper IUPAC nomenclature for this. All right, so on this one, there's a couple of different features. Here, we've got cyclohexane, so it's a cyclohexane. And we've got a substituent on here that is a carbaldehyde, so it's a cyclohexane carbaldehyde. So we'll put carbaldehyde. So cyclohexane carbaldehyde. And then here we have a benzyl group. And again, that is benzyl without the O, because this is not, it's not a carbonyl, it's benzyl. So we need to determine where these go. This is going to be at position 1, 2, and then the rest are 3, 4, 5, 6. They don't really matter because position 1 is going to be the carbaldehyde. And one last thing is that at that 2 position, it is trans to the carbaldehyde, so we will put trans out front. So we'll have trans to benzyl. So trans to benzyl, cyclohexane, carbaldehyde. So that's a nice long name there. All right. On this next one, we've got this whole functional group here, right? And that we can refer to as acetophenone. That's a commonly used name. So acetophenone, and that's that whole part there. And then we just have to remember that that's going to be the 1 position. So the nitro is going to be at the 2 position. So we'll refer to that as 2-nitro. All right. And we could refer to it as orthonitro, but I'm just going to call it 2-nitro. So 2-nitro acetophenone. All right. Next, here we've got this aldehyde, and that's going to be at carbon 1 because it is in a chain there. So that will be at carbon 1. We'll refer to this as carbon 2, 3, 4, and we can do 5, 6 or 5, 6 since it doesn't matter. I'm just going to stick here. So 5, 6. So that is hex and now. So that's hexanal. At the 3 position, we've got an ethyl, and at the 4 position, we have an ethyl. So 3, 4 diethyl, and that's everything. So now we can put that all together, and we can refer to that as 3, 4 diethyl hexanal. All right, so there's the 3,4-diethyl hexanal. All right, here we've got an enone because we've got a ketone and a carbon-carbon double bond present. We want to number from the side that will give our ketone the lowest number. If we number from this side 1, 2, 3, 4, 5, from this side 1, 2, 3, 4. So we're going to number from the left side here. 1, 2, 3, 4, 5, 6, 7, 8. All right, so that is a it is an octanone, but it has an alkene, so it's an octenone. So when we put that all together, we'll get oct, and then so 1, 2, 3, 4, 5. It's in the 5 position, so 5-ene and 4-one. And then we've got 2 methyls, one at the 2 position and one at the 5 position. So we'll refer to that as 2, 5. And I said the word 5, and then I wrote down the number 4. Let's fix that. So 2, 5 dimethyl. All right. Oct 5-ene 4-one. And that gives us the name of that particular substance. And then finally here we've got an aldehyde that also is an alkene, so it is an enal. Again, we want to give that carbonyl carbon the lowest possible number, so that's 1, 2, 3, 4, 5, and 6. So that's hex. And then the ene is at position 3 between carbons 3 and 4. So it's at position 3. So 3-enal. Remember, we don't need to put the number for the aldehyde because the aldehyde is always assumed to be at carbon 1. So we don't need to do that. We've got a couple of ethyls here. So we've got a 3,4-diethyl. And we've got a 2-methyl. So I'll put 2-methyl. So now when we put that all together, ethyl's going to come before methyl because of the whole alphabet thing. So we'll call this 3, 4 diethyl 2-methyl hex 3-enal. All right, and then that gets us the whole name, an unambiguous name. All right, and so I am I am going to go back and look at this one real quick because I forgot one little detail. And the one little detail that I forgot here is at carbon 5, we do have a specific stereochemistry. So between carbon 5 and carbon 6, that carbon-carbon double bond, if we look, we have to assign EZ designation to this, the EZ configuration. We look and see which one has a higher priority, carbon 4 or the methyl. It'll be carbon 4. And if we look at carbon 6, the two things that are attached are a hydrogen here and carbon 7. Carbon 7 has higher priority than the hydrogen. And since 4 and 7 are trans to each other, this is the E configuration. So out front, we're going to put at bond 5, so put 5E, close parentheses, and then a hyphen. So 5E or hyphen 2, 5 hyphen dimethyl oct 5-ene 4-one. So I forgot that. On this one, we don't have that concern because carbon 5 and this ethyl group are equal priority, so there is no cis-trans chemistry. There's no diastereomer of this. All right, so let's go back to our in-class assignment here. All right, so when we're looking at properties of aldehydes and ketones, so the properties of aldehydes and ketones, we are going to find that aldehydes and ketones, because they have that carbonyl, they do have dipole-dipole interactions. So they're going to have melting points and boiling points that are generally higher than alkanes and alkenes, which only have the van der Waals interactions, but somewhat lower than alcohols that we saw back in chapter 9. All right, so they'll have somewhere in between. All right, in the next chapter, we're going to look at carboxylic acids, and we're going to find that they have hydrogen bonding, so they'll have much stronger interactions. For solubility, we will find that the smaller ones, so smaller aldehydes and ketones, tend to be water soluble. So, for example, acetone, which has 3 carbons, quite soluble. Methyl ethyl ketone, which we talked about, has 4 carbons. That one's also pretty soluble in water. When we get to 5-pentanone, or when we get to 5 carbons like pentanone, we start to get to that point where it'll dissolve a little bit in water, but it may start to oil out at higher concentrations. So we'll have like a phase diagram for that. And if you get to more than 5 carbons, you're going to have tough luck getting them to dissolve. So that 5 carbon rule, that's usually about when you'll start to see a significant drop off in the solubility somewhere at around 5 carbons. All right, so let's go on to the next page where we're going to look at IR spectral properties. So when it comes to the IR, aldehydes and ketones both have the strong carbonyl peak at about 1700, although they're at slightly different positions. And I'll show that to you here, right there. So aldehydes usually have the carbonyl peak at about 1730, whereas the ketones, it's at about 1715. So it is difficult to distinguish which one is an aldehyde and a ketone solely based on that carbonyl carbon. So I wouldn't rule out a possibility just based on the one peak. There is something interesting that does happen with aldehydes, and we'll look at propanal here as an example. With propanal, there is a carbon hydrogen. That carbon on the carbonyl is sp2 hybridized, and that carbon hydrogen stretch shows up at a different position than we typically see carbon hydrogen stretching. So, for example, when we see carbon hydrogen stretch on an alkene, it typically shows up from 3150 to 3000. But for the aldehyde, we'll either get 1 or 2 peaks depending on the compound. we'll get one or two peaks, one at 2700 and one at about 2830. And that's something that's kind of unique for aldehydes. It just has to do with that particular bond being a little weaker, and so it has a lower frequency vibration. All right. Now, for ketones, we can observe that there is an effect caused by angle strain or ring strain. So the ring size will affect the carbonyl absorption in a fairly predictable manner. Now remember, ketones, they typically show up at about 1715, that carbonyl stretch. But as we increase the ring strain on a cyclic ketone, we're going to find that will increase the wave number and also the frequency. And that's because that bond is a little bit stronger when we have greater ring strain. So our carbon-oxygen bond in cyclopentanone is somewhat higher than the cyclohexanone. Cyclohexanone, there's very little ring strain that's involved here. So it's at about 1750, your typical ketone. But for the cyclopentanone, we end up at about 1745. You'll see that the ring strain has caused the wave number to go up by about 30 reciprocal centimeters. That's a pretty significant increase. In addition to that, if we go a little bit further and we go to cyclobutanone, we're going to see that one goes up by about another 35 reciprocal centimeters. And again, that's because of the angle strain. It causes this bond to be a little bit stronger, the carbon-oxygen double bond to be a little bit stronger, so the vibrations are at a higher frequency. So we'll get 1780. So ring strain definitely has a significant effect on the frequency of our carbonyl stretching, or the wave number, if we like to think of it that way. We also get what we refer to as a conjugation effect. And this one requires that we look at a couple of resonance structures. So we're going to look at this particular ketone. This is a methyl vinyl ketone, or we could refer to this as, let's see, but 3-ene 2-one, or methyl ethyl ketone, or methyl vinyl ketone works pretty well. So this is an alpha-beta unsaturated carbonyl compound, meaning that we have a carbon-carbon double bond directly adjacent at the alpha and beta carbons that are adjacent to the carbonyl, which means that we can draw additional resonance structures that show delocalization. So one of our resonance structures is to kick that pair of electrons out to the oxygen, and when we kick that pair of electrons out to the oxygen, you'll see that we now have a single bond between carbon and oxygen, positive charge on the carbon, negative charge on the oxygen. And then we can kick this pair of electrons over to now have a double bond here. We still have that single bond going to oxygen, and then we have delocalized the positive charge out to this carbon. We're going to talk about that delocalized positive charge a little bit later in this chapter. Actually, we talked about that in the previous chapter, sorry. That's what, when we did 1.4 addition versus 1.2 addition. Anyway, that is that. But now let's look at this. So we now have two resonance structures that have carbon-oxygen as a single bond. Now, of course, this structure is the best structure, and so it's going to contribute the most. But because there is some single bond character to that carbonyl, that means it's longer and a little bit weaker than your typical carbon-oxygen double bond. With a longer, weaker bond, that's going to cause the wave number to decrease by about 30 reciprocal centimeters. So we'll find here in some direct comparisons, here we have cyclohexane with an acetyl group on there. So this unconjugated ketone at about 1709, that's pretty typical for a ketone. Remember, 1715 is sort of our typical range, so that's very close. So 1709 for that carbonyl. But when we replace that cyclohexane with a phenyl group, we're going to find that it shifts that frequency from about 1715 down to 1685. So that's down by about 30 reciprocal centimeters. Same thing here. Here we've got cyclohexanone, and here we've got this alpha beta unsaturated carbons in between the alpha and beta carbons. And you'll see, again, almost perfect. It looks like it's perfectly there. It's 30 reciprocal centimeters less. So having conjugation will decrease the frequency and also, therefore, decrease the wave number. And the whole reason for that, again, the rationale behind that is that by having these carbon-oxygen single bonds as some of our resonance structures means that our overall structure has less double bond character, so the carbon-oxygen is a little bit weaker, meaning that it's going to have a lower frequency, lower wave number. Let's look at number 9. We'll switch over here to number 9. And we want to rank these in order of increasing frequency. Well, we just did a couple of these, and so we can actually label these with the correct numbers. But the one that's going to have the lowest number is going to be this one because it's conjugated. And we saw a minute ago that this one was at approximately 1650 or 1685. So this one was at about 1685 reciprocal centimeters. So that's approximate. And compared to this one, that it's about 30 less than that. This one is approximately 1715 reciprocal centimeters. And then we saw this one a little bit earlier, and it was at about 1745 reciprocal centimeters. All right, so this one has a lower frequency and therefore lower wave number than this because it's conjugated. This one is sort of our standard. It's just a standard ketone. And then this one that is the 5-membered ring, cyclopentanone, has an increase in the frequency and the wave number by about 30 reciprocal centimeters. So the order for this is going to be B is less than A, which is less than C. That's the order. And again, the rationale is that B is conjugated, so it's lower. This one's sort of normal. And then C is greater because of the ring strain. So let's look at aldehydes, our proton NMR for aldehydes. And we're going to start with propanal. So here's propanal. And the very first thing that we'll notice is that the hydrogen that's on the carbonyl is very deshielded. That carbonyl pulls a significant amount of electron density away from that hydrogen, which deshields it. When we deshield it, it goes further downfield. And downfield is going to be a larger chemical shift. Well, it's so far downfield, it's in between about 9 and 10 parts per million. Turns out there's not much that shows up between 9 and 10 parts per million. If you've got a peak down there, there's a pretty good chance it's an aldehyde. Now, as far as the location of these other ones, one note. You'll notice here on this peak, it almost looks like a singlet when we don't look at it close up. But when we zoom in on it, you'll see that it's a triplet. And the reason that it's a triplet is that it is adjacent to 2 hydrogens, but it's a very subtle triplet. What that tells us is that the coupling constant between this hydrogen and these 2 hydrogens is very small. And so typically between your aldehyde hydrogen and the alpha hydrogens, that coupling constant is only going to be 1 to 3 hertz, which is very small compared to typical coupling constants that we see. If we come over here and look at here, it's essentially an ethyl group. So our typical ethyl group is that this hydrogen on the end is going to have a triplet, and that the one here would have a quartet. Now you'll notice that we don't have that quartet blown up. I wish we did. If we looked at that quartet, we would see that each one would have these little shoulders on it because of the small coupling constant. So really what we would get with this one would be a quartet of triplets. So that one would look kind of cool. All right, one last thing is that this peak that is on the hydrogens directly adjacent to the carbonyl, that's going to show up in the 2 to 2.5 parts per million range. That's very typical with hydrogens, alpha hydrogens adjacent to carbonyl, so the alpha hydrogens. So we're going to find that that's true on pretty much most of our carbonyl compounds: aldehydes, ketones, carboxylic acids, esters, acid chlorides, amides, all of those. When it comes to the carbon NMR, there's one peak that really stands out. And so we're going to look at these peaks here. We're going to call it carbon A, B, and C. Carbon A is an alkyl carbon. It's way down here, or way upfield in that range of 10 to 20. All right, this is very typical for a carbon that's not very close to an electron withdrawing group. We have one that is the alpha carbon. It shows up close to 40. That alpha carbon, not unusual for it to show up in that range. The one that's really interesting, then, that really stands out for both aldehydes and ketones is the carbonyl carbon. Remember, the carbonyl carbon, we can identify it on the carbon NMR. And so here, you'll notice this one is at 203. It's very common for aldehydes to be out here in the 200 to 210 range. For most of our carbonyl carbons, they're somewhere from 190 out, well, usually about 180 out to 220. But this one is going to typically show up for aldehydes near 200 to 210. Ketones also close to 210 or close to 200. All right, the adjacent carbon, I already talked about this one. It's close to 40, and again, that's pretty common. So the one I definitely want you to be able to recognize is the aldehyde carbon is way out there, close to 200. So there are a couple of interesting aldehydes and ketones, and we're going to go through these, and then we'll end this particular video. So we want to look at some interesting aldehydes and ketones. We're going to start with formaldehyde, and there's a couple of reasons we'll start with formaldehyde. One, it is a very common compound. It's produced in billions of pounds industrially, and you get it from the oxidation of methanol. So produced in large quantities. Often it's sold as a solution in water called formalin. And when it's in water, it's actually in the form of something we call methane diol. I will explain that a little bit later when we talk about addition of H2O across aldehydes. So acetone is a common solvent. We talked a little bit about it. It shows up in like your fingernail polish remover, but it's off in a lot of different paint strippers and all kinds of industrial solvents. It is quite flammable, so it's something that you have to be careful about. And we'll also find that your body will produce a small amount of acetone, particularly when you're very dehydrated. So when you get very dehydrated, it's common for you to get a really weird taste in your mouth, and that really weird taste in your mouth is going to be, or it can be, the acetone. And it's very small quantity, so it's not like you have some solvent showing up in your mouth, but it's enough that makes you thirsty. And it's particularly if you're exercising and you start breaking down fatty acids, you'll definitely start to notice that. All right, there are some other interesting aldehydes and ketones that have distinctive odors to them. And one of my favorites is vanillin. And you can extract vanillin from vanilla beans if you get 100% pure natural vanillin. That means it comes from a vanilla bean. That usually costs more. You can also get synthetic vanillin. You can use that in your kitchen as well when you're flavoring things like, making cookies or whatever. But it's a very pleasant smelling compound. I really like the smell of vanillin, and so that is a commonly used in cooking, and particularly for desserts and things. Cinnamaldehyde, you can get it. Here's the sort of the structure. It's got an aldehyde here. There's a carbon-carbon double bond, and then there's the benzene ring. It gives you that particular odor of cinnamon that you're familiar with, and it comes from cinnamon bark. In our labs, we do an experiment where we take cinnamon bark and we'll do a steam distillation. So we'll break up the cinnamon bark into really small pieces and we'll heat it up in water. And we'll do a steam distillation, which means that water comes over, but also the cinnamaldehyde will come over with that steam, and you can extract it. And then when you extract that with a solvent, you can get the cinnamaldehyde out of the water mixture, and you can isolate that cinnamaldehyde. Again, very pleasant smelling compound. There's citronellal, which comes from lemongrass. Included in that is the citronella grass, or you can get citronella extract. But anyway, the citronellal, that particular compound that comes from different varieties of lemongrass, has a very pleasant lemony odor to it, and also is a moderately effective mosquito repellent. Now, citronella candles, I'm not sure I would trust them to repel mosquitoes, but there is a mild mosquito repelling factor there. The geraniol also comes from lemongrass, and there are a variety of lemongrasses, but you can isolate that from there, and it also has a lemony odor to it. All right, there's one last category that I want to talk about with carbonyls, and that includes some of these steroid compounds. So steroid compounds are going to be hormones that come that have a carbonyl in them. So many of the steroids do. One example of this is cortisone, which is a naturally occurring one. It is secreted by your body's adrenal gland when you have some sort of injury, and so your body will release the cortisone. It is naturally an anti-inflammatory compound that shows up in your body. And of course, if you get inflammation, you can also get a cortisone shot that helps to reduce the inflammation. And then there is a synthetic analog to that, which is called prednisone. Instead of having to isolate the cortisone, you can get the prednisone. And prednisone, really the only difference here you'll see is this double bond that is on the prednisone. And it's also a very effective anti-inflammatory agent. Now, I'm going to mention this. It does not mean that it is 100% safe. So you should always talk about it with your doctor, whether you need that prednisone. So if your doctor recommends it, you should probably do it, but you don't want to take it just willy-nilly. Taking the prednisone, it does have some effects. For example, as an anti-inflammatory agent, it can decrease and the way it works is it decreases your immune system. It sort of weakens the immune system so that you don't have such a strong inflammatory reaction. Well, the downside of that is that it does weaken your immune system. So it can increase your risk of getting infections. Again, I am not a medical doctor. You should only talk to medical doctors about which medicines you take. All right. I'm going to stop there, and our next video we're going to pick up with talking about preparations of aldehydes and ketones.